Welcome back, everyone. Our next talk actually has two speakers, Connor McNamara and Jasmine Bertram. Both are researchers here at IDA. They are in the Sustainment Group, focusing on tasks for the Defense Logistics Agency. So today they will be speaking about improving readiness outcomes with collaboration, quantifying the cost of siloed resourcing. Yes. All right, take it away. I'll give you 5 minutes.
Thanks so much. So to start here, I'm actually going to try to explain a bit for everyone about what this whole sustainment system is about, how the supply chain functions. Good. So I want you all to consider a hypothetical situation. You and I have been both tasked by a healthcare company to run operations for their different parts. They've given me the purchasing decisions for a hospital, one hospital for a large city. You, on the other hand, have been given the task of purchasing for all the urgent care facilities around that hospital. So say 10 facilities. Initially we're buying a lot of the same stuff, the small cheap stuff, gauze, IV bags, needles, etc. The small things that everyone's going to need and can easily store, kind of cheap too. Well, you're looking at what the reports from the doctors and nurses have been saying, and you've been seeing that they occasionally, not too often, but sometimes have been referring patients to me to use our MRI machine. And you think, okay, that's normal, but there's a bit of a wait time. They're not getting it immediately, maybe a few days, maybe a week, possibly a month, depending on how bad things get. So you look at your books and go, okay, how can I make this faster? Well, an easy one is, well, I'll purchase an MRI machine. The issue is, you have 10 facilities. You can't just say, oh, this one's getting it. You need to make sure that every facility gets one. So that's a massive investment of costs. You might not have the space to do it. You might not have the actual people who can actually do this. You need techs. You need a lot of extra concept on top of it, on top of the pure capital. So that's the kind of mindset we want to think about when going forward with this whole talk of how do you decide where to place items? How do you best use your money? And as part of that title, that siloed decision, how are you making decisions when you and I aren't talking to each other? I'm only looking at my hospital side, and you're only looking at the books for those urgent care facilities. So, another example here is, in general, how are we... Oh, this is freezing. But anyway, how is the supply system supposed to work in general? So, consider a family, and all families are going to be a little different, but you're going to see that a family frequently is buying some of the set items. So your groceries on a normal, routine basis, weekly, bi-weekly, however it is, but it's more or less the same amount of money and closely the same items every time. Well, there's also going to be extra items, those high-value tickets, those rare occasional purchases that have to be considered. And they want to just buy it from one store easily. But they're not alone. There's other families, and those families have their own demands that are different. Some similar, but generally a different makeup of what those items are. And again, they want to go to one store. They want to go to Costco and go to a store that sells both a car and, apples. And you want everything in one-stop shopping. Make it easy for yourself. So that local store must have those items that the actual family needs and can cover everything they want. But they're not alone. There's multiple families for each of those stores. Different sets of demands. Some same overlap, some different overlap. A lot of different items, some different, but where are they getting from? Well, that's their centralized distributor. So they're buying it from a wholesale that is then putting it into those local retail locations, and then you, the end family, are buying from those local retail. That issue here is that, again, wholesale is only seeing the demands coming from retail. They don't know what the end user is actually purchasing. They just see, in this example, in total, we see 4 avocados. So wholesale knows, I need to have 4. I don't know where they're going. I just know that they're getting split up between these two. They could have one per family. They might have, 1 a quarter. We don't know, depending on the purchasing cycle these things are on. So these are some of those unknowns in the whole system, is who's using what, when, where. Again, you can make inferences from your actual purchasing data from those retail locations. But inference is not the best idea for actually how the system should function. Again, It's a bit simplified for what we're going to be talking about, but it gives you the idea of how this is split up with a centralized wholesaler that is going to be distributed with localized warehouses that can easily send those supplies when purchased to your local retail stores. Going back to our hospital question, we have that bit of a delay with the MRI machines, and you are considering, how do I fix this? Well, maybe I've already fixed it. Maybe I've already purchased a second one. Maybe this is just a delay that you're seeing that's temporary. Well, I'm getting it set up. Now, your decision could actually make this completely bad for both of us. Now I have two. I'm not going to see that demand. You've spent an absurd amount of money trying to do this. So both of us are now down from where we should be. Or, in a different case, maybe one of mine broke. And, it was broken when I got into the job, and it's about to be fixed. Again, this isn't something that you would know unless we're talking to each other. These are those unknowns in the questions that we're going to be considering with this for the whole system for naval aviation is where I want to take this to. This is what the rest of it's going to be about, is naval aviation. So we have a similar setup in this one where we have a wholesaler and retailer in this case. So our wholesaler is still a warehouse land-based system. So multiple warehouses on land that are going to be sending occasional shipments to the actual fleet. Our retail locations are going to be carriers in this case. And again, you need to have an important piece. Well, warehouse, you might be able to do it by just having two. Two is all you need. Due to the demand rate, you can easily reorder within the time people want it. It's a low cost. So say if it's a $1 million piece, $2 million is all we had to spend. But if you then try to stock that at retail, you're going to need $10 million worth of stock, one on each ship. Again, that's a much larger investment than just that two. Well, maybe it might be needed. Maybe it has a really long lead time. Maybe we need it desperately. It breaks all the time. It's best to have it there. Well, that might be the right answer. Or it's something that we can actually work with this. This is a whole spectrum we need to consider. There's no one set answer for this. It lies somewhere on this from all wholesale, all retail. Maybe that is the answer. Or maybe it's a mix somewhere in there, in the gray area. And it's going to depend on the part, on what the demands are. Part of it is space alone. So we have to consider all these factors when thinking about this. And with that, it is made frequently in isolation, these decisions. As I've been talking about with that example of you and I working at the hospital, we're not talking to each other. And that's what is happening here in the actual DoD is those wholesale and retailer, they can kind of infer, again, from wholesale can kind of infer a little bit what's going on, but you don't know. So again, we're making decisions blindly. We're making decisions that's best for us, but that might not be best for the whole system, and it might actually not be best for you based off of what's going on in the other party. Due to that nature, as I said, with how it broke. If my MRI machine broke, it's going to be fixed. It'll be back up and operational, but you are trying to fix a problem that's not a problem. So we have tried to look into what the effects of doing this wrong are. And that's the key, is stovepipe sparing decisions can lead to suboptimal outcomes. We wanted to actually try to quantify in dollars, and we were able to. That was our novel finding, is we're able to tell you the actual dollar impact for making an incorrect decision this way. So in this cartoon here, I want you to consider this is an optimal setup. So in this situation, those two in our warehouse for these four carriers, this is the perfect setting. We worked it out from that 1,000-foot view. We were able to see the whole system. This is how it should be. Well, some terrible situation happened. Your budget's been slashed in half at wholesale. Now you can only buy one. And that now impacts the readiness for for the platforms on those carriers. Well, what do? Well, it really comes down to two options. And I think we all know that one option is a really terrible decision that no one would actually take, which is just say, okay, fine, we don't need those platforms. Those planes don't need to go out. No problem. We'll just wait. What's really going to happen more often is that you're going to try to fix the problem by throwing money at the problem, as always. You're going to buy those spares for the carriers and thus increase your costs. You're not assuming you're going to ever spend that money. This is new money unaccounted for. And so not only has the total amount gone up, as we went from 1 to now buying 5 total for the DoD, the actual individual party of the retail location is now buying 4 where they were previously going to buy none. So what does that look like? When we actually worked this whole out, so you can see this is a fully notional notional example based off of actual results that we ran for multiple platforms. So for this platform 1 here, when we were cutting from 90 to 80, you see that there's actually an increase in cost. So for every dollar we cut, we're going to spend $1.15. So in red there, we have increased overall spending to regain that same availability of aircraft we had. And this is not a linear cost. It actually is, it increases as you go. As you see, it actually compounds from that 9 to 80, 80 to 70. Those add up and compound upon each other itself. So that's just those individual cut prices we see. You might be looking, what's with that blue? What's going on with the blue? Well, that actually is a place where a cut is okay. You were actually overspending in this situation at wholesale. So that's the other side of this. We can actually find those issues where, we found that regime where you're like, okay, I can actually cut this cost a bit. I can do some cost savings for there and maybe allocate those funds differently, buy smarter with your money. Versus that red, that's a cost overrun for everyone in the end. It's not smart. We've not allocated funds properly. But using our end-to-end simulation tools, able to quantify the exchange rate between retail and wholesale spending for a range of different weapon systems. And we are able to fully quantify this. Look at how is our money being spent smartly? Where are we accidentally increasing costs for retail and thus DoD in general, but at that retail side, or potentially the reverse of this, retail funding has been cut, we need to make it up wholesale. It works both ways depending on how you want to look at this, but there is an optimal place that we can try to be, but we can also see what the actual economic impact is for going off optimal. And with that, I'm going to pass it over to my colleague Jasmine.
Oh, okay. Sorry, which button? Okay, so Connor was talking about the need for optimizing resource decisions across different levels of our supply system, right? So like, what do I put at wholesale versus what do I forward deploy to retail? In the second half of this presentation, I'll be talking about making optimal resourcing decisions across weapons, like across multiple weapon systems, all of which are, players in our larger DoD supply system. So the motivating question is, how should the DoD allocate its resources when buying spares to support the readiness for multiple weapon systems? So you can imagine, or you don't have to imagine, the DoD has a variety of weapon systems, all with different functions, different configurations, they all utilize different parts. And so how should the DoD decide how much money to put towards buying spares to support the readiness for, its portfolio of different weapon systems? Well, this is hard for two main reasons. The first is that each weapon system costs a different amount of money to achieve its, relevant or related readiness target. Also, the DoD has a fixed and limited budget for buying spare items to support the readiness for these different platforms. So, that requires trade-offs to be made between platforms. So a dollar spent achieving a readiness target for platform A is a dollar that you cannot spend anywhere else. And so for both of these reasons, this is a hard problem to solve, but it's also an important one to not solve in isolation, right? So you don't want to make resourcing decisions looking at each platform individually. Instead, we propose that the DoD needs to evaluate the impact on all of its weapon systems when making these resourcing decisions. So what I'll show over the next few slides is how we propose that the DoD could use quantifying the cost of readiness for the different weapon systems that it supports as a basis for both evaluating and optimizing its resource allocation strategies. So to start, a little primer on how exactly we would estimate the cost of readiness for a given platform. So we'd start by generating optimal sets of spares given a certain budget amount or a certain level of spending. So in the Sustainment Group here at IDA, we utilize a stock optimization algorithm called readiness-based sparing. It's been around for a while, pretty widely used, but there are certainly others. So, pick your favorite stock optimization method of choice. And so we'd say, okay, for $200 million, plug that into optimization method. It would spit out a laundry list of items to buy for that amount of money. Do this again for $300 million, it would spit out a slightly different list. And we can continue doing this, generating optimal sets of spares for different funding levels. Then we can take our set of spares, plug it into a discrete event simulation that models the platform's operations, maintenance strategy, the structure of their supply system. And for a given set of spares, we can estimate the readiness level that we would achieve with that set of items. So, pick your favorite readiness metric of choice. Here we were choosing the percentage of our aircrafts that would be available to carry out their missions. And so we can just repeat this process, generate a bunch of different optimal sets of spares, all costing different amounts, run them through our simulation, get the respective readiness level that we would achieve with each one, and we have now empirically estimated the cost of readiness for a given platform. This is the exact same premise as like a cost effectiveness curve, if that is more relevant in y'all's work. I just want to call out one part of these curves is where our readiness return on investment plateaus there on the upper right. So this represents the point where buying or spares are no longer the limiting factor in achieving more readiness. So as you can see, if we were to continue investing in spares, we don't really get any gains in terms of readiness. Other factors such as manpower constraints, scheduled preventative maintenance, the inherent reliability of the system, those are all the factors that come into play, in terms of getting greater and greater readiness. And I call this out because this point will vary by platform. So again, contributing to that idea of the cost of readiness is different for different platforms. So again, getting back to our motivating question of, how should the DoD decide how much money to spend on each platform or to spend on the spare items for each platform, we can quantify the cost of readiness for each platform. So, in the example that I'll be using here, imagine we have 4 platforms. We've gone through that exact same process to quantify the cost of readiness for each one, and the corresponding curves are there on the right. So what I'll walk through in the next couple of slides is, how we can both evaluate different resource allocation strategies using these curves, and then I'll also show some examples of how we can actually optimize a resource allocation strategy using these curves, and specifically the data points that comprise these curves. So to start out with, an easy, simple, straightforward resource allocation strategy, imagine the I love all my children equally strategy of uniformly funding. So saying, okay, we're just going to put the same amount of money per aircraft in this case, or per system, to buy spare items for each system. So, we may get an allocation strategy that looks something like this. So for $550 million, for example, we're achieving 40% availability on our aircrafts. Well, how does this actually play out in terms of readiness impact to these platforms? So you can see, not super well. So for 2 of our platforms, the one in black and the one in blue, we're actually past that plateau point on our cost of readiness curves, meaning that we've likely overfunded these platforms. And then by comparison, the other 2, we have not even reached that plateau point. So in addition to using these cost of readiness curves to evaluate an allocation strategy, we can also use them to optimize. So if, for example, I said, okay, for the same amount of money, I want to maximize the amount of readiness that I achieve, we set up a linear program, an optimization model to do just that. So our objective function was, maximize my percentage of available aircraft subject to, my cost constraint. Running that through, you guys have probably already pointed out the flaw in, such a naive and I suppose simple linear program, but, it completely doesn't fund one of the platforms. So this is actually, I suppose, a cautionary tale type example of the need for tuning your optimization model based off of, the relative importance of your platforms, any operational constraints that you may have. But this is, one methodology that we could use to optimize our allocation across platforms. Lastly, just one more example. So let's say that, we were good with the level of readiness that we were achieving under the uniform strategy, but we said, can we do this for less money? We can just, change up our linear program or our optimization model, and we might get an allocation strategy that looks like the one on the right. And again, we can evaluate the readiness impact of such an allocation strategy using our cost of readiness curves. So the takeaway here is that there isn't one correct or single correct optimization function. That, again, would depend on the relative importance of your platforms, any operational objectives or constraints that you may have. But I just wanted to highlight, one, the need to make decisions considering the impact on all of the weapon systems that are benefiting from your supply chain, and to also highlight that in tying the resource decisions to your readiness outcomes, you're also enabling your organization to drive your budget decisions with your operational objectives. And then just to wrap up, I wanted to highlight the underlying methodology that was common in both the analyses that Connor and I presented. So in tying resource decisions to readiness outcomes, we were able to solve these pretty complex problems. And the way that we were able to do that is using a series of modeling and simulation tools that we've developed that look at the end-to-end sustainment system. And that's really key, right? Because we want to know how resource decisions made at the top level of our supply system, like all the way up at our wholesaler, are impacting what's going on, all the way at the other end of the system at the operational level. And we're able to also evaluate, all the touch points in between. So with that, thanks for your attention, and happy to take any questions if we have time. Yeah, thanks.
Hey, thanks for the presentation. One of the things that I mostly work survivability and lethality, and one of the things that I'm constantly wrestling with is when you're running any kind of assessment in this vein is the idea of planning for the actual employment of the system, right? So if you're optimizing readiness for a peacetime condition, that's not necessarily optimizing for a wartime condition. So how do you effectively build error bars around your use cases, given the idea that you do need to plan for readiness in both peacetime and wartime?
Yeah, certainly. And I know this has come up on other projects within the sustainment team. So with these, end-to-end simulations of, what's going on supply-wise, what's going on operationally, and, modeling all the dynamics in between, it actually affords the flexibility to say, okay, right now I know that we're operating, at this op tempo currently in peacetime, but what if we were to dial up the number of flight hours we're trying to get out of our planes, steaming hours, so on and so forth. And so model as flexible as, like the ones that we have and like the ones it sounds like, other services are using would allow us to do that. Now, we would still certainly rely on subject matter expertise to tell us exactly what that wartime scenario would look like, right? Unless there's like some sort of historical data on what exactly that elevated op tempo is or that elevated operation status is, that's something that we wouldn't be able to obviously pull out of these simulations. It would have to be more of an input from subject matter experts. Does that cover it all?
Yeah, I should have stayed back there.
Okay.
You see a lot of wishful thinking, and especially going back to historical data, that can be really deceiving. If
Totally.
you're trying to model what's happening in the Red Sea based off of what happened in the Gulf War, you would be getting totally different answers right now. So
Yeah.
it strikes me as a complicated problem that we're going to have to keep going after. But I
Yes,
appreciate that the model allows you the flexibility to build that in.
Yes, certainly.
So I think this is for your partner in crime. You had a little star on your slides about optimal purchasing assumption. I was wondering if you could kind of scratch at that a little bit. What does that mean? What does that look like? How does it play out?
Okay. Oh, yeah, that was
there. Yeah.
Yes. Okay. So that optimal purchasing strategy, and what we mean by that one is that 10,000 foot view. We're able to look at the bigger picture. So for a set readiness target that is told to us by experts on this side, we can actually using our simulation tools is kind of tune in what those purchasing decisions should be at wholesale and retail to obtain that readiness outcome. So just buying that, crossing that threshold of for us, that optimal is enough with a little bit of leeway. So that's, we've purchased enough to hit that target and a little more to be safe is basically how we're looking at it, is where you can comfortably operate to keep a set readiness target.
Cool. Hello, I'm Frank from IDA. Thanks for the great talk. As they say, there's no perfect model, so I was wondering, how often do you see your simulations in the real world kind of overlap or not overlap?
So supporting DLA, we haven't done a whole lot of verification and validation of these models. We actually have another group within the sustainment team that works with NavAir, I believe, to validate the models. So I'm unfortunately not super familiar with what that process looks like, but I do know that they work pretty closely and update these models with new data pretty frequently. So maybe can point you, since you are also here at IDA, can point you to who would be a good point of contact for that.
And in general, so from what we've been seeing from these purchasing decisions, from looking at when we run it on our side, we have been getting fair agreement with the experts at the different locations and different groups that our readiness, what we're ending up with from our models is pretty. We have good agreement, so it's in that good enough for government work.